Hi, my name is Murad Ramazanov, and today we will go through assignment from through the homework 2 from the computer organization and architecture class. So this assignment is all about reverse engineering. As we can see, we have hexadecimal numbers right here, and we have 15 of them. So that means that after doing reverse engineering, after working through this assignment, we will get 15 lines of code or 15 lines of instruction. So we start our process with converting this hexadecimal number into the binary number, and we will get 32-bit binary number. And all the work will be done on that 32-bit binary number. We will work on this number. We will identify the types of the opscode types, etc. We will identify immediates, arrow values. All this will be done using 32-bit binary number, and then we will get the instruction itself. We will use separator to test our instruction to double check is it right or not. And we'll work through all of them, so 15 of them to get full picture of this assignment. So let's go. I used Excel for these purposes. I found Excel very useful and very convenient because we can divide it and we can see that on the left side. Okay. Yeah. So on the left side, we have hexadecimal numbers. They're in the yellow boxes, and under them I have my instructions. That's the final instructions that I have got. And on the right side, this is the space for my reverse engineering. This is space for the 30-bit numbers, and all the conditions, all the commands, and all the register stuff. So all the working process is shown here on the right side. So I'll start with the first one. As you can see, we converted this number into the binary number. We get this 32-bit binary number on the right side. And we'll start with the first 4 bits because these first 4 bits are responsible for the condition. And we know from the table, from the slides, that this 1110 means that this is unconditional. So it's always executable instruction. Then we have 00. So OP is a data processing. So it means that it has something to do with the math. It can be the add, it can be subtract, or with the AND or operations. Then we have the 1, which is immediate one. Immediate is 1. So that means that we will work with numbers, not with registers. Then we have our command, CMD. And again, from the table in the slides, we know that this particular CMD is representing the move instruction. We have S0, which means that the flags will not be updated. The NZC flags are not going to update. And then we have 4 bits for both of our registers. That's the RN register, which is 0, and RD register, which is 1. So this is the destination register. In the case of a move operation, and not only in the move operation, but overall in any shifting operation, it can be the logical shift left, it can be the logical shift right, etc. These shifting operations, we ignore our RN value. It's a 0. As we can see, all bits are 0. Because in this kind of operations, we need one source register. For example, in the add or subtract operations, we need to have 2 source registers. Here we just use one, which is the R1 in our case. So we ignore this RN register in this case. Then we have 12 bits remaining, and this 12 bits, so this 8 bits representing our immediate value, which is 0, right? These 8 bits represent the immediate value, which is 0, and these 4 bits represent the rotation, which is 0 as well. So this is our explanation. This is my explanation of the first line, and let's just double check it. So let's just copy this one. We go to the separator, and yeah, let's just cut it off. So here's our function, our instruction. Let's just compile and see, did we do it right or not? As we can see, yeah, here our instruction move. We can see here's a hexadecimal. It's the E3A01 and 3 zeros at the end, and this is the same as we have. So after each line, I did this double checking. So I did the line, then checked it with the separator, and get the satisfaction of doing it right, doing the reverse engineering right. We will not do it for every instruction because it will take too much time. It's time consuming. I did it for the first one here in the video just to show how it works and how the process is finalized. Next instructions are the move instructions, and they're pretty the same. So I mean the conditions, they're all data processing. The commands are the same, even the flags are the same. The flags are not updated. Errand is ignored as well in all of this. We just change our immediate values. For example, here we have 10, here we have 5, here we have 0 as well. and just changed our distinction registers R2, R3, and R4. So these instructions are pretty identical in their structure. Then we have five, yeah, our fifth instruction. We have again always executable condition. We have the data processing. Here we have a difference. We have immediate value as zero, is set to zero, which means we will work with the registers, not with the numbers. CMD is changed. It's now is a sub CMD, so we do some subtraction. And S is changed. S is one right now. So this means that we will update our NCC flag. So we will not use sub, we will use sub S, right? We have our Rn value, which is not ignored. In this case, we use it. So it's a R3 and we distinction register is a R5. This part, so it's a source 2 part. We have hw2, which is 0. So we don't have any shifting because it's a 0. We don't do any shifting. We have shifting type, left shift, logical shift left because it's a 0, 0, but we don't use it here because it's all 0. No shifting. So that means there is no change in shifting. There is no steps. So that's all 0. I just put it here for information that it's just a shifting type. This is a hw5, but in this case, in this particular line of code, it doesn't matter because it's all 0, so we don't do any shifting. This 0 is a hard-coded one. I denote it as the HC. And this is the RM, our value, which is R4. And we get at the end this code, R5, R3, and R4 in this particular order. Here's the instruction with the add. We change our condition. Now it's less than condition. It's still data processing. It's still the registers. It's now add instruction. Don't update the flags. Rn are the registers. Both of them are 0. The same situation as in the previous line. We have hw5, but no shifting, no any operation of that. So it's all 0. No left shifting, no right shifting. Yeah, it's all 0. Hard code is 0, and we have our Rm value, which is R2. Yeah, so even in this case, yeah, I didn't actually show, but even in this case, we have, for example, no, in this case, we have I1, yeah, so it's the immediate value 1. We have the immediate value 1 here in this case because all these 8 bits representing this immediate value, and we have 0 for the rotation. I saw it was a immediate 0 and I didn't show all these steps, but it's actually immediate 1, so it's right. Then we have the new operation, the new OP is the branching operations. Condition the same, less than condition. Hard-coded 1, and we have 0 for the L, which means that this is a branching instruction, and it just branches to the new address. So it goes to the new address, but it forgets where it come from. So we don't have any return address for this particular situation, right? So it's just L is the B. It's just a branching. We don't use any link registers, and the branching instructions are pretty easier to do work with because we have immediate 24 field. It's a big field, and we need to do two's complement on that field because this field actually represents the number of 4 byte steps from the PS plus 8. So we actually find what we do the two's complement of that. That means that we do inverting. So we change 1 with a 0 and we change zeros with ones. I didn't put all zeros here because it will take too much space. So I just decided to focus on this particular last 4 bits. As you can see, this will change to 0, 0, 1, 0. So, and all this will be 0, and it doesn't matter. It doesn't play a huge role here. So that's why I just skip this part and focus on that. So we'll get 4. We'll add 1 because it's 2's complement. We will get 5. However, because it starts with a 1, it means that it's negative. That's why it's not a 5, it's negative 5. So we're kind of going negative. So we're kind of going 5 lines back. But, however, we don't need to forget about the program counter because program counter is always ahead. It's 2 steps ahead. It's 2 instructions ahead. That's why we can actually do a shortcut. We can say that it's negative 5. We add plus 2 because of program counter. We will get minus 3. So it's a 3 lines back. And we can show it using the bytes because in RM32, every instruction is like 4 bytes. So negative 5 multiplied by 4 will get negative 20 bytes. And then we again use the program counter plus 8. So we do 8 plus 8, we get negative 12. And then we again divide by 4 and we get 3 lines back. So this is a branching to 3 lines back. This not the issue. This kind of instruction is the same. The difference we have with the L is 1, so we'll have a branch with a link register. So it saves address of the next instruction within the link register. So here we have a B, here we have a BL with a link register. And this field is pretty the same. So it's all 0. 0 plus 1 is 1, but because we start with the 1, it's negative 1. It's multiplied, again, it's short, it's plus 8 because of program counter, and divided, and we get the one line forward. Here's an instruction with the memory. So it's the 0, 1, it's the memory instruction. Again, with always executable, no condition for that one. And here we have, instead of immediate value, we have not I, which means that not I is 0, so I is 1. That's why we will have the immediate value here. Then we have our P, which is the pre-indexing, and I would like to correlate with this W, which means that's the write back. So in this case, we have P and W is 1. So that means we will have the pre-index instruction. We can see here we have an exclamation mark and the brackets. The U is 0, which means it will be subtraction. The B is 0, which means uh, it will be the 32-bit 32-bit word, like it will be fully a 32-bit word, because if we have B1, we will have, for example, store B, or we have LDRB, so we will use 1 byte, which is 8 bits, but here we have full instruction. And we will have L. L is 0, which means it's not load, it's the store instruction. Again, we have the registers, RN register and RD register, and we have source 2, which is 4 in this case. Now here instructions are the move instruction. They're pretty the same as in the beginning. We just have different immediates, different destination registers, but all these commands and the conditions are the same. They're remaining the same. The add instruction, yeah, again we have sham5 is 0, so no shifting. Hard coded 0. I just should put it here, yeah, just to align it well. Yeah, so it's hard coded 0. And it's a sham5, it's the 00, so no shifting. So it's just abstraction. We have S1, which means it will update flags. Here we don't have it. There's no updating flags. So that's the last instruction. Yeah, that's the branching. We have L0, which is just a branch with no link register. Again, we calculate, we're inverting all this. We get the I just wrote down the end as well, just to focus on that part. So it's a 7, -7. We multiply, we get the final lines back. So this all about reverse engineering. Let's just check this with the simulator. So yeah, here's the code itself. So as you can see, here we have. I actually was naming them B1 and B2 during the reverse engineering, and then I just chose to stick with the B1 and B2, which means block 1, and this is the block 2, due to simplicity, so it will be simple to understand it. So there's like two blocks. The first one B1 and the second block is B2. So the first block is the loop, but it's a conditional loop because we have b less than b1, so it will come back to the b1 with a condition. However, the second loop, as we can see, we have just b2. We have no conditions. As we can see here in the code itself, in the 32-bit binary number, we have condition always executable. So that's why just the b. It doesn't have condition for that. So it's the unconditional loop. So this loop will be going forever. It will be going forever. And the problem with the crash itself, is that so it starts with the store instruction. So we subtract 4 from our R13, which is the stack pointer, and the R14 value inside the 14 will be stored in the new address. So this will actually grow the stack itself because we're pushing that onto the stack. So basically we go through the loop itself, then we come back, we go through the loop again. So it subtracts. It's every time subtracts and writes the value, subtracts the value and writes the value. There's no change. So the stack keeps growing. It keeps growing constantly. We don't remove anything. We're just pushing it in the stack with this unconditional loop. And at the end, at some point, it will have some invalid address, and it will have some memory problems because it will try to go to the restricted address, or it will try to use invalid address, and which will cause the stack overflow in this case. So this is the fault. This is the crash of the program because of this unconditional loop B2 block 2. Let's just check it. Let's just compile it and see what's going. Yeah, what's the problem? Yeah, as you can see, we have some memory problems. Yeah, so it use more memory because I think it's growing. So the stack is growing. It runs out of the memory. It runs out of the RAM, and it attempts to override a restricted memory address, right? So it's going outside of that and tries to access the restricted area, the restricted address. That's why we have some memory issues here. So that's the crash of our problem. That's the crash of our program itself.